Hello. Happy Sunday. Hope you're enjoying your weekend so far. Thanks for coming to my stream if you're already here. We'll get started in a few minutes. Meantime, if you join the chat, say hi. Post any questions you have, as always, at any time or suggestions. I'm not perfect coder, so I'm going to miss things from time to time. I appreciate the feedback. Just to recap where we were last time, we were looking at point reads. So that is to say, fetching an individual key from the B tree database. And we had implemented it wrong. So we're going to look at fixing that. And if we get that done, maybe we will wrap this up and look at Elixir. Doing this in Elixir, I think in some ways it should be substantially easier in Elixir. But I'm rusty with Elixir, so I'm not sure yet. There's also one other thing that I'm considering doing. It's kind of a little personal story. But an old colleague friend of mine has noticed that I'm doing this series on Berkeley DB, partly because I just post on all my social networks about it to invite you all to join. And turns out he was on the team at Sleepy Cat when they were selling Berkeley DB in the late 90s. So this is long before the Oracle acquisition and all the mess that comes from their ugly attitude toward open source. Let's just put it that way. And it really tickled his fancy. So he sent me some stuff that he's working on that's really interesting. And we may look at that in the future. But also, he worked with, back when we were both, we're no surprise, we were both at Basho Technologies working on React years ago. But he worked with one of our partners at Trifork while we were there on a new storage engine, which is called Hanoi DB. And you're like, what does Hanoi have anything to do with it? Well, it was a level, so like Level DB or RocksDB is what I think most people use nowadays. You have tiered storage, so the most frequently changed keys or most recently changed or created keys are in the lowest levels. And then as those low levels fill up to maximum size, you combine all of the files at that level into a larger file that gets promoted to the next level. Anyway, so it's sort of like that. But what's really interesting is that it was in pure Erlang. And what made it interesting and different from things like RocksDB, LevelDB, is that it would have only two, or I think it was like level time or level to the power of two files per level. But there was always +1. So as things were compacted and promoted to deeper levels of the database, they would move to this side file. And so what happened was that they were trying to understand, how this is working, what the performance looked like, and he developed a visualization of the files that were actively being written on disk, and it looked like the implementation of the towers of Hanoi. So that's how it got its name, Hanoi DB. Anyway, we might look at implementing that because that's, I think, really interesting problem. And it'll get into some of the details that we won't get into the series on Berkeley DB because there just really isn't the content from that blog post or that blog series that we've been following to cover those sort of deeper things. For example, we're doing things pretty naively in our current implementation. I'll just flip over to it. Like our database is just a flat buffer of the entire file. We're not dealing with multiple files. We're not dealing with transactions. We're not dealing with page cache management. So there's a possibility that trying to implement something like HanoiDB would expose some more interesting problems that we could dig into and all learn from. So that's sort of the direction I'm thinking. And I mentioned the other project that he was working on. He has a compressed, he calls it sparse, a bitmap index. Hi Chris, thanks for coming to the stream. And it's written in C, so that he can use it in a database that's implemented in C, or database engine. And we might look at that, because that's really interesting. It involves like bit shifting and masking and all sorts of things to get like huge space efficiencies. But anyway, let's get started on where we were. I think I've kind of let this set of warnings creep up, so maybe we'll get started cleaning those up first, and then let's look at fixing this. This was our implementation, and well, it didn't work. We're gonna have to review what we did, because honestly, it's kind of probably mind bending for me, and we need some other, maybe we need some other implementation for finding a key. So this is possibly too complicated. Anyway, let's look at our warnings and see if we can't clean any things up. Okay, so this is easy. We didn't use iter tools. We have it, but we can get rid of that. Yeah, I'm not worried about that not being used. We can put it back in here later. I might turn off warn dead code in the future. Walk is never constructed, because we're not calling it from main. No big deal there. I think this is why all these warnings exist. Maybe let's just put that back in for now and see how many warnings go away. Okay, quite a few. Yeah, let's just let's print a bunch of the one pane editable results in Z is amazing. Yeah, sometimes it trips me up though, because it like there's not enough context. Ooh, they added that. I just noticed this. So one thing that always bugged me in previous versions of Z, I'm by the way on preview, so I'm always on the bleeding edge, which I have not yet regretted. But it used to be that like you could be here and you couldn't open the whole file from being on this line, but if I click that, I'm going to the actual place, which is good, because before it was like, well, you have to click this, but then it takes you to the first one rather than the one that you had your cursor on. So that's an improvement. Yes, I'm very happy with Z, Chris. I know you're still on VS Code for good reason, but yeah. Okay, so this bit is interesting, and let's go to the. We have a bunch of unused fields in the entries. Now I think we commented out overflow because we're not. Well, first of all, the docs are bad. We couldn't determine which one, or like in what cases it should be an overflow entry and not internal or key data. But this length, I think is it's needed in the implementation for C, because C doesn't have slices, right? Here, let's just do it right here. Right, so length, the length of the variable size data field. So this is telling us how long this is. But when we've deserialized it, like when we've created an entry, we look at the length. We pull the length out, and then we use it to slice the source buffer. But now that, the length of this is embedded in the slice, that's part of the Rust type. So I'm wondering if what we should do is just remove that. Like, it's not useful in our implementation. And I think that's a reasonable thing to do. And we can do the same for internal. If we look at, so overflow, we skip over. Again, there's some stuff in here that's like, not sure what we do there. Right, so this is key data item length. So this is, this key is like, what's the first key of the page that this points to? And so we don't actually need that. We have the slice here. We've sliced it when we construct this variant. So let's just remove that. Now the type, number of records, that's just a matter of we're not accessing those fields. So I think that we can remove that. And again, here we're using the length there. Right. And we don't really care. Yeah. Okay. So there's some additional things we could fix here, but let's first just make a let's change this into a match. Let's see if Rust Analyzer can do it. Yep, cool. I showed that to a colleague the other day. They had a match in their code. I think they were using like Copilot or something, and then I was like, hey, Rust Analyzer can turn that into an if-let, and they were just, their mind was blown. It's like, yeah, this is what good tooling does for you. Okay, so the only other option is internal, and I don't know that there's a useful display for this. Let's figure something out. And this doesn't have to be a big deal. Maybe we just say return right. And I think I want to get rid of this. Yeah, that probably makes sense. And then we don't have to use return. We can just make an else here. And let's say data.len. And we're going to write to the formatter. Hi, Isaac. Welcome. Thanks for joining the stream. My day's gone pretty well so far. I was able to sleep in. I got my lawn mowed, and then I'm here hanging out with you all. Okay, so what do we want to display when we print an internal entry? I think we need to do something like this. But let's go not const. I've been doing too much TypeScript, dang it. So let's say let key is if let okay from UTF-8 data. Then we'll say s, and that should be a stir. Otherwise, we'll do like format similar to this, right? Let's just do this. We just want to show that it's binary data of certain length. And then we can say ty is the type. The type is always btree though in our implementation. And there's some question in my mind about whether we should make those like an enum. And when we load this, we turn this field into the enum. Right now it only have one. Let's see. So we could say page no. Thanks for your opinion, but that's not really helpful. Go back to NeoVim. Okay. And the number of records is let's say records, say nrex, and we'll say first. This is like, this is a display thing. This is for individual. So this is like printing to people versus debug, which is kind of printing to programmers, to people who know the internals of the code. So we can say key. It's not great. We can, I guess, ignore ty. We'll just do it like that for now. I would like to do those things we just talked about. Get the type into an enum, and then we could just print the page type. First key is not true, actually. maybe it's lower bound, or minimum key, right? Because we saw in some of the data that the key picked for that first key in the page is not necessarily the actual first key that's in that page. It might just be, this is a lower bound that the database engine arbitrarily picked. Okay. So that cuts down on some stuff. Let's look at some of the other warnings that are in here. Right, we're not calling walk from anywhere anymore. Let's just put that back in main for fun. We can just do this. Now, interestingly, because we implemented display on entry, we can just print these out, right? Easy peasy. So that should hopefully cut down. Why has Rust Analyzer not picked that up? Move to next page is never used. Oh, did we change our implementation of iterator for walk? Interestingly, we did. Did we create move to next page for the... No, we wouldn't have for the... we wouldn't have done that for the finding individual keys. This is private, so it would only be accessible in this file. Yeah, let's just I think that this is just unused. So let's comment it out and maybe we'll remember what it was for originally. Okay, I mean, let's just print it here. And then move on. We do need to hold on to that because it is essential to the database format. Okay, and then we're doing stuff like, I think this was part of our original iterator. Is last page, right. We know it's the last page if it's the level is 1, so it's a leaf, and then the next page number is 0. Honestly, I think we know that if the level, it doesn't matter what the level is. It would be the last page in that level. I think this was a termination condition for a loop previously. Let's comment that out for now. Okay. Right, so there are fields in this variant that are not used. Yeah, again, I think for this, it's essential that we capture all of this. It's interesting that our stat print thing doesn't print these fields. Okay. Yeah, because we're constructing all of it here. Let's look back at that stat print function. What did we do in there? Okay, so this is actually looping over. I don't know why it didn't. We don't need to do this twice, right? Because it's printing them here. I don't know why I was warning about that walk never being constructed. Maybe it was just me misreading that. Okay. I think the answer for these is we go here and we say allow dead code because they're going to be accessed. They're going to be accessed to be constructed. They're never read, at least not yet, because we don't have writing done, right? So now there's no problems. Okay, I feel a little bit better about that. It's not great. And here's the other thing: is like this debug prints this. Why does it not think that those fields and those variants are never accessed? They're freaking printed. Oh my. Okay. So we need to fix this. So if we run, right, so we're getting the walk here and the stats and the different pages and whatnot. Okay. What we're not getting is finding individual keys. So I feel like I would like to trace through this. So this is calling db get, right? And then it's just printing key not found because we didn't find anything. Excuse me. Okay, let's just start putting in debug statements. Right, we're going to look at the header. Oh wait, that's a U size. say self.page, current page, header. Okay. Interestingly, oh, okay. So what we were doing here, we should get the root of the tree, right? Because this is looking through all the pages in the database. And if it's a metadata page, which should be the first page, so this should just work on one step of the iterator. Then it'll get the index of the root page of the tree and return that. Otherwise, it's going to return none. So it'll be interesting to see if we get to this spot or if it's returning none right here. I think that shouldn't be the case. And then we should see that this is a B tree page, right? Yeah. And so its first one should be like, we're looking at internal pages. So let's endure the warnings again for a bit. And we're going to just try to find all the B's. Okay. So it gets a B tree page, page number 1, right? We get that far. Okay, so let's debug prev. So it should have found a page number if the key is greater than or equal to data. The thing is, there's no guarantee. This is probably where we went wrong. There's no guarantee that... Oh, okay. No, actually. So if key is greater than or equal to data, we know that it's in at least this page, right? So this is fine. But if key is less than data, then we know it was in the last page that we captured. And if it's none, so we're looking at the first entry here in the internal page of the tree. If we're looking at the first entry and key is less than data, then we know it's not in the database. Okay. So it occurs to me that something that we're not handling is the case where we run out of entries and we should move to the next page. The thing is, though, the tree is total. So like there's a root page, whether it be a leaf or an internal page, that contains the entire key space, right? So if key is greater than everything in that root page, then the only thing we can do is try the last page found that the key is greater than, right? So gosh, I wish I had a sketch thing. This would make this a lot easier. So let's, okay, so the goal of this is to find, is there any page that we should try that's a child page of this? So like it's farther down the tree toward the leaf. And as long as key is greater than everything in that set of internal nodes, then we know we need to go down on that last page. So I think this is fine. Let's figure out what this turns out to be. And of course, you know, if it's less than, we break, and prev should be none, right? Or it should be whatever the thing in the middle is. Okay. So let's look at that. Okay, so interestingly, did I not save that? I bet I didn't save it. Yeah. Okay, so we need to debug the previous page. Okay, so it says it finds page 2. So we should go to page 2. We're in page 1. We should go to page 2. So when we hit here, the question in my mind is, what we're going to do, let's just put that here. We know that we're getting the root page here, so that's fine. Let's debug the page header here. I don't need to borrow because debug wanted to consume that. Okay, so we get page 1. We get through that iteration. It says go to page 2. We get page 2, and it is a leaf page. Okay, so we know level 1 is a leaf page. Every internal node above that adds a level to this level number. Okay, so then it scans and it doesn't find. So I think the problem is not in our traversal. So we can be pretty confident with this, I think. The problem is in this. So let's debug offset. Actually, that's a U size, isn't it? Yep. Okay, so here's the next thing. Let's remove this question mark and put the question mark here, because I think I want to see, I wonder if there's an issue of equality. If our key that we're searching for is not equal to key data. Let's debug key data here. And then let's maybe not debug that yet, because I think I want to see if the issue is we are, you know, iterating over this incorrectly. Maybe it's this ×2 here, because we're stepping by this and the position is over this iterator, not over the original. Let's figure out if we have like some off by 1 garbage here. Okay. And that was not so good. I don't want to debug. I want to front line key key. Yeah, let's just debug offset. The other thing that we can do is we can debug page dot. What do we have on page? Header. Yeah, let's do that. We're gonna have to borrow that. Offset is option usize, so it's copy. We don't need to borrow it. All right. Okay, so we know there's 24 entries. Offset is none, so it didn't find any of them that match. The other thing that we could do, we could just rewrite this, because I think what I was trying to do is be clever about like find the equal one and then pull out the value. But we could potentially iterate in chunks of 2 over entries. Let's try that instead. And let's do it as a simple for loop. Page.entries chunks 2, right? And let's say key is pair 0, else continue. And then we could say if key is key data, those are equivalent, then we will return pair sum pair 1. Let's see. We need to get the value data in it. Yeah, so then let's do something like this. We'll say let entry key data value data pair 1, else unreachable. You better not have uneven numbers in here. The other thing is we could put panics in here as well. I think it's almost pointless, but okay. So if the key equals key data, then we should have a value for it, and the signature of this is return an option of a slice of U8. So we should return some value data. And then if we get to the end, this is way simpler, by the way, we return none. If we get to the end of that and there's nothing there. Okay, so what's the warning? Show me the money. Okay, the trace in 2 chunks is not oh, I didn't pull in iter tools. I removed it because we thought we weren't using it. Okay, so it should work now? No. Is not an iterator. Why is into chunks not an iterator? Do I need to do into iter? What am I doing wrong here, Rust? Oh. is this where we need to do the tuples thing? Here. So I was kind of under the impression this was like the slice, that when you do chunks on slice or windows on slice, it gives you a slice with that number of entries in it. But we could do value tuples, right? And this needs a turbofish. Come on, Sean. There we go. Okay, and then we can say this is key, and this is value. What's wrong here now? Any code following this expression is unreachable. Binary operation cannot be applied to entry. We're not trying to do that. Oh, okay. So I overwrote that variable. Let's call it key entry and value entry just to be clear. And then it won't shadow our variable that we put in there. Okay, and now we have an issue with overlapping borrows. Fun. And I think that this is why we didn't do a for loop earlier. Because we had issues with this thing is temporary, and you know, the issue is like this page is fine to return from, but it's borrowed through this iterator, and I think it doesn't like that. Okay, so let's go back and try our position thing. I have to go way back. Okay, we're going to get rid of this. This is the part that we started adding. And the compiler is very unhappy about. Okay. Let's just print out those entries as we go through them. Okay. So it says key not found, but there's that very first entry. I wonder if we just have a typo. It's shorter. Of course it is. Okay. So let's see if we can find it this time. Haha. Okay, we found it. The issue was our main code. Okay. Hurrah for debug. Ah, yes, the wrong number of B's. Yes, exactly. Okay. This is why you don't trust blog posts. Okay, so we're actually finding the thing, right? Note that it's found at index 0. Let's re-enable, like, this one obviously should be, this is not. Anything that's in our, here, let's put that print back. Anything that's in our database is just repeated characters of the same key. So this should not be found. We expect that to not be found. Okay. So let's run that. I've removed some of the debugs, but it's going to print out everything that it's scanning, right? So it found key data, right? And now it's scanning for KJS HD8, right? Okay. And it doesn't found it. Interestingly, you would think in terms of ordering, it should stop looking after this one. So but what this with this algorithm, we are going to scan all keys in that leaf, which is not what we want to do. So we have a suboptimal thing here. Um, we could do, rather than position, we could do enumerate with find map. Let's sketch that out. Okay, so let offset, yeah, page.entries. So we still need to iterate through the entries. Let's do enumerate. So we get the index step by 2, right? And let's do find map. So this is going to be index entry, right? Because enumerate always puts the index and a tuple on the first, and the type system agrees. Okay, so we'll do an if let. The thing is, this is still going to iterate through all of them, and I think that this find map is going to iterate through all of them, right? We need some way to break early. So I think that we need to go to, like, find map is kind of what I want. I want to like compare this and get out the index. But if we find that key is less than the value there, we need to break. Because otherwise we're just going to scan all the entries in that page, and that's not what we want to do. While let? Maybe while let would work. There might be too many conditions in that while let. Like, we need to destructure this thing and do the comparison. Yeah, let's, okay. Let's look at iterator. I think there's probably either here or in filter or in iter tools, there's probably something we can use. Yeah, we don't want map while. What's scan? No. Try it. No, that's nightly only. Of course it is. Position. Position what we were using before. Yeah, that's not what we want. Okay. I just have to do some stuff manual. Let's bail on this. So I think I want something like let offset is none. None. Okay, and then we're gonna do for index and entry in page.entries .enumerate step by 2. Okay. So then what we can do is we can say let entry key data else break. You know, if it's not a key data, then we, you know, what are we doing? This should actually be unreachable. I'm going to do that again. This is looking somewhat similar to what we did before, but now we can say if key equals key data, then we say offset is some index. Okay, and this needs to be mute. And again, this is not going to be the most else if this is not going to be the most elegant way. We just break and no, break. Now, the other way I could structure this is, rather than breaking here, we're going to say if key is less than or equal to key data, then break. Yeah. Okay. So we can get rid of this. And now we don't want offset times 2 because we've had the actual offset. And we can remove the parens. Rust doesn't require those. Okay. So then we do just offset plus 1 because I've done enumerate before the step by this time. Previously we were using position, which is like position in the iterator that it was called on, not on the original iterator. Okay, so now let's put our entry back in here. Let's say trying entry. And sure, the question mark's fine there. Is the list sorted on key? Yeah. So that is a property of the database engine. This is a B tree, so the entries are sorted. Yes, it's guaranteed by the database engine. So we know that, and I'm sorry if you missed that bit, Isaac, but here in our entries iterator on page, where is it? That's page header. So we return an entry iterator that keeps track of the current offset into the page. And honestly, it just does page get entry. A page get entry is where it's actually interesting. So if it's a B tree page, then we should allow it on internal pages. But oh no, we can't. There's no entries on a metadata page. I'm sorry. We look at. Let's see how this works again. Okay, so these are just checks. If it's a B tree page, then we can continue. Otherwise, we return none. If the index is greater than the number of entries here in the tree, then we return none. So like obviously you're trying to index past the end of the page. And then coincidentally, and this is discussed in this, entries come from the end of the page. So this offset is an offset to the end of the page, roughly. Okay, so we look at the header, and starting from the end of the header, we go, okay, so there's a 2-byte offset and a 2-byte offset and a 2-byte offset, so and so forth, up to the number of entries. And then so we're tracking tracking the offset there. So we get the offset of the previous one. This is a simple index lookup, which is nice. This is another simple index lookup, and then we slice that section from the beginning of the entry to the end of the entry. So that's how that works. But yeah, it's guaranteed by Berkeley DB that those are in sorted order, because it is a B tree. Otherwise, if they weren't sorted, it would be kind of pointless to do this tree walking thing to find a key. Okay, I hope that answers your question sufficiently. Wow, that's fun. I didn't insert that. Thank you, Rust Analyzer. Okay. Okay, so looking back at main, let's look at our new, oops. And let's just print out that and see what we get. Okay, so trying to find this, or this is the entry that it tried to match against. It found it and it printed it out. Okay, so now we hit K, and we realize the next entry is greater than the thing we were trying to find, and we stopped. So I think that fixes that algorithm there. And let's do our last one. Turn on our last test case. Okay, so key was not found. So binary search instead of linear scan is left an improvement. Yeah, so interestingly, they say in the blog post, and I think it has to do with the size of the page. You could do binary search. You could go, but sometimes linear scan is just simpler. Now we could do something like in our iterator here. We could do a binary search. There's honestly, I don't know that there's a huge value of that. If we look at how many entries there are, there aren't many. We could just say entries.len. We don't care. Oh, what did I do wrong? Oh, not len, it's count, because it's an iterator. My bad. Okay, so there's only 24 keys. Like, at that point, you're at the leaf. There's only 4K in any page, and it's going to be less than 4K. I don't know that there's a value in having binary search at that scale. Now, the thing is, though, we are sort of doing binary search in that we're traversing, well, not binary search, we're doing a log n plus scans, right? Log n level, n being number of levels. No, I'm sorry, n is number of keys, log n is essentially the number of levels. I'm not incredibly concerned about it. The binary search is going to be much more complicated. We would have to like look at what is the what is the number of entries, and then like pick something in the middle. Is it less? Go to the left. If it's more, go to the right. Okay. So yeah, it is a good question. Like, and I think there's some validity to considering that. The other thing that is weird, I think, too, about Berkeley DB is that you, like we saw here, the entries go backwards. So like in terms of cache coherence, this might be not great. You would want them to go forwards. I do see how, though, this is sort of like stack versus heap. You know, you can grow the stack from the bottom and the heap, you know, from the top of the memory space, and maybe that's why it's like this. I'm not sure. It's something I would like to ask my colleague who actually worked on Berkeley DB. Why do the entries go from the end of the page instead of the beginning? It's really strange. You know, like we had our own storage engine at Basho called Bitcask. Dead simple storage engine. There's an implementation of it in Rust, so I'm not going to do that on stream. But it was just like, hey, we're going to write right at the end of the file. And when we reach the max file size, we'll close it. And we'll open a new file. But the entire key set for where is the value for this particular entry, it was in memory. There were interesting trade-offs there in that, like, you had to tune how often it would compact, because like as you overwrite or delete entries, you get tombstones, and then those have to be cleared out when you compact so that you have fewer things to keep track of. But you know, the pointer in memory for where a particular key was on disk was just a file and offset. And it was surprisingly good. You would think, oh gosh, that's got to be super inefficient, but no, like the page caches in operating systems are actually quite good. So that turned out to be really good for like high write workloads, because you could just append to the end of the file. You were only syncing the list of keys in a file to disk when you close the file. So you always had you always had the pointer in memory, you know, to where that thing was. Anyway, I'm getting off track here. Yeah, I would love to know why this goes backwards. That is really strange to me. I think it's interesting. It probably meant that what they could do is, knowing that the header has to be at the beginning, they could not fill in some of these things while they're writing the page, dump all the entries in there, filling in their offsets as they go. And then when they're done, go in and fill in, okay, these are all the fields that we need to in this buffer. So, okay. I want to find out why this was not found, and I think the issue is let's put our print line back in here, or let's just debug. No, we don't want to do that. Actually, we want to debug entry, because I want to find out why that, sorry, not debug, we want a print line. I want to figure out why it doesn't find this S, and I think it's like the B's, we don't have the right number of S's. So let's look at this point reads and look at his test. Yeah, so you're supposed to be able to find this one. I think the issue is I just don't have the right number. So we're going to do that. We're going to cheat. Yeah, fewer S's. Okay, so we found it. So let's get rid of the prints in here. Cool. So I think this is a good place to close on the Rust implementation. Until there are more things we can work on this blog post series, there, see, he has sections for writing and recovery, things that are not written yet. And this is a couple months old at this point. So I think we'll come back when there's more content for here. We have another hour planned in my stream, so maybe we make this commit. Fix point reads. Yeah. Can you link the post in the chat? Absolutely. I've done it a couple times, but I'm happy to again. Here you go, Isaac. That is what we've been working from. Yeah, yeah, it's actually not too bad, Chris. Like, I feel like I've discovered some of the sharp edges of this. It might be fun to work through. And, like, of course, additional implementations in other languages always helps understanding this sort of thing. Now, what is curious about this, and particularly this post that we mostly skipped, is that I get the sense that there are things in the implementation of the storage format that are, what's the word I'm looking for? They're idiosyncratic to C as the language that it was originally implemented in, and the developers who wrote that C in their style. So what would be interesting is to try to figure out what are the more general things we can learn through this that aren't specific to how this format is implemented in the original C and in the open source reimplementations of it. So that is sort of interesting. Again, like questions like that. Why do the entries come from the end of the page? It could have to do with one page fits in, an L3 cache or something. I don't know. It's 4K. Like, what were we working with in the late 90s? We were working with 32-bit systems for the most part. I don't remember if this was originally implemented on like Next or maybe like Sun machines, like Spark architectures. I'm not sure about any of that. Also interesting that I guess this 16 bits for the offsets was enough to fit 4096 easily, right? That's probably why they did that. Why is this HF offset field there? I guess so you don't have to scan all this. Like, those are little things. Obviously, the type being a 1 byte number that was probably matched against a constant that they defined in their code, or like maybe even a pound define, is interesting. Yeah. Of course, the log sequence numbers, which is funny. You look at when we were debugging out the page header. I don't have enough history there. It was showing that it was like max int. It makes me wonder, do they count down? And when they hit 0, they blow up. I don't know. But that's 8 bytes. That's going to be, a 64-bit number. It would take a long time to exhaust, but still. So the log sequence number is really just about transaction isolation and like rewriting pages and stuff like that. Okay, it's probably about structural sharing too. So like you only rewrite the pages that have changed, um, and then you pick the page that has the same page number but the smallest LSN as the current page. We did it all in one go. Like if you remember this test data or gendata.py, we just piped this to db create or whatever the name of the command was, um, and so we got the whole database created in one transaction, so to speak. So that log sequence number was not at all changed. Okay, I think this is a good place to switch. Let's try to get some of this started in Elixir, and we'll just go from the beginning, and then we can end the stream. So let's do a mix new BDB Okay, you're gonna require me to do. Let's do app BDB. Okay. So we've got the scaffold here, and we've got a bunch of stuff to delete. Okay. So we can like go back from the beginning of the blog post. The other thing that we could potentially do is, yeah, let's just go through this. This is not too bad. Again, we will need to do some of this like parsing out stuff. So how do we want to begin this? We could look at our Rust implementation. Thing is, I remember we started with basically the page header, right? And it was this enum. Now, we are going to be able to do different things in Elixir than we did in Rust. Notably, we will have binary pattern matching, so we won't have to do this, right? And we can also probably let's make a new folder BDB, and let's put a new file header. Okay, and let's make a new function here, which is going to be parse. And I'm going to feel a little bit lost without types. Nope. So I'm going to start putting some in here. Spec parse. I need to take binary. Does that do arrow? I forget. Or is it colon? Yeah, it's colon. And it's going to return header metadata or B tree. And we'll make these structs. That'll be nice. Okay, so the key here is, remember, if those bytes from 12 to 16 are the magic number. Yeah, in Rust it was 2 LE bytes just because we know we're on a little Indian machine. Interestingly, in Elixir we can say native. So let's copy this. And I need to remind myself of the syntax in Elixir. Oh, that's fine. Okay. So we need to go. This would be easier in Erlang because I remember that syntax better. Let's look at binary pattern matching syntax on Elixir. Binary strings and char lists. Bit strings. Okay, so right, so we can do individual bits. You can say the size in the pattern there. Okay, binary is a bit string where the number of bits is divisible by 8. Of course, we expect that. All right, modifiers. So we can say binary size 2. Would that would do 2 bytes. Charless, whatever. Okay, so we need to find where the patterns are. I think it's in. I've forgotten where this is. It's weird that I remember the Erlang syntax and not the Elixir one, but it's okay. Pattern. Patterns and guards. Or pattern matching. Pattern matching. Pin operator. No. Okay. Variables, literals, tuples, lists, maps, structs, binaries. Here we go. Documentation for the special form. Here we go. Okay, so it's having to jump around. So bit string. So integer, float, bits. Bytes, UTF-8. Bytes is an Elixir binary. Okay. Okay, so here's where the options are. So we say integer, which is most of our stuff. Native is like native byte order. So if we wanted to say, yeah, the metadata page and the B-tree pages have the same first 12 bytes, log sequence number and page number, right? Okay. So we can say LSN is, how do we do that? Okay, colon, integer, native, size. Hey, thanks, NextLS. So that's gonna be 64 bits. Bytes. Let's start with that. And then we're gonna do, this is page no, integer, native, size, 32. I'm sorry, we're going to this. Right, so 64 bits, 32 bits. And then we could say, we could paste our thing in here. And we could just do this as one big pattern. Now, what we might want to do is just say page is the variable here, and this is page. We could match on page and start building our pattern here. Um, and this is going to be a literal native size 32. And we can just start building out the rest of this pattern here. It's going to get big, but we are not building production code that we want people to learn from. We are building code for fun. Okay, so we say version is another 32-bit integer, right? One thing that's not clear to me, I wonder if we can leave off integer and native. Let's read this a little bit. Okay. We need unsigned on all of these so that it just doesn't not interpret it as a negative number. I wonder if we could do just unsigned size. This is interesting that it's implying that big and native are the same. I don't think that's what we want to do. Right, and we can refer to other things in the pattern, which is cool. That'll be really useful for pulling out sub-binaries that are like the data inside. Yeah, so big is the default, but we want native, which should be little. What I'm not clear on is, can we just do unsigned native and not say integer? I think we have to say unsigned native, which is going to clog up. So let's do unsigned integer, and let's just copy that and put that in all the places. Okay. Yep. By the way, this is super nice. I sometimes forget how great it is to be able to just write a pattern and go like, yeah, hey, that's actually the contents of this byte buffer. Okay. So version, page size. Come on. Size 32. Another. Do we need the size on there? Can I just do a bare 32? Okay, that could cut down on things. Is that true? We could do something like this. Define it as a module constant. But we would only be able to use that for the parts that are constant, like that magic number. Okay, so let's get rid of that. Page size. Okay. And then we have EC unsigned size 8. I want to say that yeah, I don't think I can abbreviate it like that. I want to say that by default it assumes it's an integer. That would make sense. Here, let's just pop this over to the right so we can see it at the same time. Okay, ECTY unsigned size 8. Again, for bytes, that unsigned might not be necessary for single bytes. Okay, and then we have a skipped byte. That is one thing to remember about this. You can see over on the right, we had MF is byte 26, and then we jump to 28. So free is another one of these. Last page no is another one of these. Yeah, I'm tempted to go like put this in a module constant and go U32, call it that, and call this one U64. I'm not sure if I can do that. We'll find out later. Okay, and we have end parts, and we have key count, and we have record count, and we have flags. And then we have UID, which is this is bytes, size 20. Does that sound correct? UID. Okay, so it starts at hex 34 and goes to before hex 48. Yep. Okay, let's see here. Min key is another one of these. RE-len is another one of these. RE-pad is another one of these. Root. Crypto magic. Okay, so now here what we need to do is we need to get the checksum. Interestingly, we did a U28 128 there. We can probably leave that as bytes in Elixir. We don't need to turn it into a number. But we need to read what they say. So the gap resumes on byte 460. And I think that what we ran into here was like, what's the end? The end is 92. 460 minus 92, 368. So we need to do ignored. Size 368. And then we have crypto magic is one of our integers again. And then we have IV is a 128. Now we could avoid turning this. We could just say like size 128. I think that might be smart. We don't like IV is an input to a cryptographic algorithm. It doesn't necessarily need to be a number if we were actually going to implement it. And then finally, checksum is going to be 20 bytes. Okay. And it got rid of my pretty formatting. Okay, so then what we're going to do is we've pulled all this out. Let's go ahead and define, and this is, I need to do this, right? And then we'll define all these fields. So header metadata, do def struct, and we're going to go, this is going to have LSN. I think I have to do a list like this. LSN, I've forgotten how that works, because I don't do Elixir day to day, even though I love it as a language. Page no, version, data size, page size? Why did I say data size? Is it page size in here? It's page size. Let's call it page size. EC TY MF free last page no end parts key count record count flags UID min key RELEN REPAD root crypto magic IV. Okay, so now we have I'm sorry, we need IV and checksum. So we just defined a struct here that contains the metadata header. Okay, and then yeah, so this is like we need to handle the other page type, which is significantly simpler. So this I'm just going to say BDB header and this is going to be rote stuff. I've named them the same thing that they should be named, so unfortunately some kind of boring coding right now. I was thinking about this. Somebody has probably written a library that will do this for you. But that's all right. It's like probably called binary struct or something like that, if I had to guess. It's important to remember here too that since we've already done this before, we know that the rest of the page for the metadata page is undefined, and we just need to ignore the contents of that. So bear that in mind. Flags. And what we'll do probably to wrap up the stream after we get this metadata one written is we'll make a little script, we'll open the database, read the first page, and try to parse the metadata struct out and you know, print it out. And we can probably just do that with IEX if we yeah, that's probably the best way to do that. And then we can see what the contents of this are. Flags, UID, min key. Love it when the LSP helps me. RELN, repad. And hopefully the compiler will say if I missed any of the fields. Okay, it's not complaining. Let's do a mix compile real quick. Oh, I need to be in the right directory. Okay, so yeah, it doesn't like that I defined this in the same file, but didn't define it first. Let's just make a new folder header, and then it can figure it out. Metadata. The other thing that I haven't done recently is I have not updated my version of Elixir and OTP. So OTP 27 is available, Elixir 117 is available. We could potentially do that and get some nice stuff. Okay, so key checksum is not, I typoed it. Yep. Okay. Yeah, okay. So let's just make a new file, btree.ex, and we'll do def module bdb.header.btree and def struct and give it the empty list. I don't think keys are stored in sorted order. Okay, that's an interesting assertion. The problem with that that may be the case for that particular thing that you have there, but like B trees don't work unless they're sorted, right? So I think that I would need to check some things there. The data used in the blog is sorted when inserted. Yes, absolutely. The data used in the blog is sorted when inserted. That's how they designed that script. I don't know what your head thing is. Okay. It looks like Twitch has kind of blocked out some of the words in your message, but maybe there's an assumption in DB load that the data is already sorted by key. That is a possibility that DB load expects its input to be sorted, which is a weakness. And if it's not sorted, then ouch. Yeah. Within a leaf. But like that's the thing though, is it should be like, otherwise all of the guarantees you have about finding a key within log n time is bunk if you don't have them in sorted order. So Okay. Okay, conflict found. Here, let's mix clean. Oh, I didn't delete it from here. Did I? I didn't, yeah, because I didn't save it. Okay. Okay, so let's say okay db is file dot read. Okay. Okay, so we read the file. Let's see if we can. Okay, so it doesn't match anything. We got a case clause error. Let's look at, let's say header size 512. Okay, so there's probably something wrong with our pattern here. Oh, there is something wrong with this pattern. Need to do binary. Okay, so let's look at header. And that is 512 bytes. Now, I actually want to do binary size 512. Okay, so that's better. So if we look at, let's just pass the header. It's still probably going to say case clause. So we should see the magic number starting. Yeah, it would be painful if you could only insert sorted data. I think there's probably some other thing that I'm missing about that db load command. Let's have a quick look. No harm done. db load. Okay, so the input to db load must be in the output format specified the db dump utility or specified for -t, capital T below. Okay, so this is the caveat probably here in this option. The T option, capital T option, allows non-Berkeley DB applications to easily load text files. If the database to be created is of type B-tree or hash, or the keyword keys is specified as a set, I don't know what that means, the input must be paired lines of text where the first line of the pair is the key item, second line of the pair is the corresponding data item. Okay. A simple escape mechanism where new line and backlash, record separators. Okay, and dash lowercase t says, you know, B-tree or hash or whatever. Yeah, it doesn't say that it has to be sorted. That's really curious to me. I would expect, yeah, it would be painful if you could only insert sorted data, right? I would expect that that would be not the case. Okay. So, um, let's ignore this for a minute. Um, how about we make a simpler? I kind of went whole hog on this, right? How about we make a simpler one to start and see what we're getting? Because we should see similar output to what we were getting on the rest side, right? Um, now, possibly it's this native, and we need to here. Let's replace native with little and see if that fixes the problem. Reload, reload, or recompile. Okay. Yeah. Okay. It still doesn't. Um, I feel a little bit better about using little on there. But maybe what we can do instead is let's make a version of this and just get the first few fields, right? And see what those are. And yeah, let's call this magic. Oops. And then rest binary. And then we can just return that as a map and see what we get. Because I think that there's probably some. Yeah, I know it's not used. We'll fill in stuff as we go. Okay, so we're getting the right log sequence number. We're getting the right page number. The magic, let's see. That is correct. So that should match. There's probably something else there that's not matching, which is likely something like this unused byte. So let's start adding in those other things and see what we can see how far we can get. And the match on this is getting a bit much. Okay, so let's get version. Just do this step by step. Okay, so version is 9, which is sounds about right. Page size. Oops. Page size. 4096, what we expect. That's interesting though. One thing that we didn't do in the Rust version is we just assumed that they were 4096. We could probably say read the first 512 bytes of the file like as a safety thing before we do anything else. That was not part of the yeah, that was not part of the assignment. Okay, so now we're getting to single bytes. I honestly don't know if we need the unsigned there, but let's try adding these. And we got EC, EC, TY, TY, MF, MF. Interactive. It's so good. Okay, so type 9 for B-tree. Okay, so now there's the bit where there's the empty byte. So there's an unused byte there, which we just ignore. Let's get free. Okay, so this might be wrong. We should look at our Rust version and see what it says. So let's do, does our stat print out the metadata pages? Yes, it does. So we should be able to compare that by turning that back on. Cargo run. Cargo run. Okay, so if we go up here, okay, here's our metadata page. We get version 9 data site. Free is 0. Okay, so that's correct. So at least we're on the right page. Haha, we're on the right track there. Okay. Can you wrap that formatter, please? My aging eyes. Okay, so we got free. We get let's just do 3 of these at a time. Let's see. So free, end parts, key count. Now, if I had to make another guess, what I would guess is that it's this ignored block. The rest of these are fairly straightforward. Let's just keep on chugging. Okay, last page no is not used. Okay, free. Last page no. End parts. Key count. I already got key count. Okay. I already have end parts. What am I doing? I just didn't add last page no. Okay. Okay. So the last page number is 4. That looks correct. This is page number 0. EC and MF are 0. TY is 9. Yep. Free is 0. Last page number is 4. End parts is 0. Key count is 0. Record count is 0. We don't have record count yet. We're almost there. Let's go ahead and get these in there. Again, line length. And then we have flags. Formatting, failed to format via language server. Okay, we'll use mixed format in a bit. Okay, so we got flags. Flags are 0 on the original. We also added record count, which is also 0. Record count is 0. So far we're doing okay. All right, now the fun stuff. So UID byte size 20. Oops, that needs to go in the pattern. We are iteratively narrowing this down. Okay, and what do we get? Interesting. So we're off. So this is probably where our problem comes in. That starts 74, 87, 74. This one starts 59, 110, 74, 8, 17. What are we doing wrong here? Flags is 32 bytes, or 32 bits. I wonder if we got 0 here by coincidence on some of these. Interesting. I want to replace magic with this now. And we'll get rid of that and see if this still works. And then we can try to debug what's going on there. Yeah, that's still working. It's still matching. We didn't get a bad match there. Let's see. We're running out of space here. Okay, UID is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 bytes as I expected. Yeah. And then here we've got one, yeah, let's see. $26. That's 20 bytes. It's interesting we're getting something different. I wonder if it's... No, that wouldn't make sense. These are just bytes, right? So they're unsigned. Why will we get something completely different? Like, because this is 74 to start. They both end in 6 zeros, it looks like. Yeah. Going back. So that says 163. Sorry. Fighting with my editor for a second. That says 163, and this says 152. I don't see any relationship between those numbers, which is really strange. 218 versus, yeah. Now, maybe the issue is that I'm reading a different file. So yeah, let's do let's read the one. Let's read that one. Okay. That way, at least we're looking at the same file. Yeah, okay. Now we got the same thing. Yep, I wasn't opening the same file. Okay, so at least we get some consistency there now. So that UID looks correct. Let's get these other numbers in there. And then we should wrap up. Kind of running out of time on my day. Okay, UID RELN. We need min key. I've already got RELN. We got REPAD. Root. Okay. Comma. Okay. So unfortunately that these come out in a different order, whereas in Rust they are strictly ordered by the order that they are in the struct definition. So we're gonna have to jump around a little bit to compare. Can I do side by side? Will you let me? No, you'll let me drag it up here though. Okay. So min key is 2. Uh-oh. RELN is, yeah, we've got something wrong here. All right, I think this is a good place to stop for today. We can resume doing the Elixir implementation next time. What I wanted to show, which I don't think that I successfully did, partly because Elixir's syntax for this kind of pattern matching is much more verbose than Erlang's. But like, we can slurp out the entirety of that struct without writing the individual conversions ourselves. In this case, it's not true because we've got to specify everything. But we can do one expression versus what we did over here in the Rust code, which was take individual slices, try to convert them into the types. Yeah, again, I don't know that this is any better. I think I perceived that it would be easier in Erlang or Elixir. I think that assumption did not hold true because the default endianness, probably for legacy reasons, of the Erlang VM is big endian. Maybe it was network applications. The matching is still really nice. Yeah, like especially if it doesn't match, it blows up. That part is super nice, I have to say. Now, one thing that we could do potentially is in this function, instead of doing the whole big match here, let's do like find the magic, and if the magic is there, parse a metadata, otherwise parse a B tree. That's something we can do. And then we could put the slurp out all the fields over here in this file. That might be a nice thing to do. Okay, let's wrap it up for today, and hope to see you all next week. And if you're based in the US, hope you have a nice Independence Day on Thursday. Otherwise, I'll see you next weekend. Cheers.